All right, in section 2, we're going to start talking about a different type of function, which is called an exponential function. Now, an exponential function is kind of a function where something grows by a set amount each time, but instead of adding that amount each time, it is multiplied. So a very traditional example of an exponential function is if I start with an amount of money. Let's say I start with $2. And let's say I start it two ways. We'll do a linear growth and we'll do an exponential growth. So in a linear growth, I just add the same amount each day. Let's say I add $3 each day. So I have 2, I add 3, I get 5. I add another 3, and I get 8. I add another 3, and I get 11, so on and so forth. In an exponential, instead of adding by a certain number, we multiply by a certain number. So instead of adding 3, I multiply by 3. So 2 times 3 would be 6. Times another 3 would be 18, times another 3 would be 54. So one thing that exponential growth is really known for is it grows really fast. Linear growth, where you're adding the same amount each time, grows pretty slow. Well, exponential growth will go very, very quickly. So an exponential function, as we define it, is really going to be any function of the form f of x or y equal to a times b to the x. Now what's different than a linear function or a quadratic or any of the other functions we've seen, we have the variable x in the exponent. Now this is not the only type of exponential. So an example, I could have 2 to the x, which is one we'll do here in a little bit. So y equals 2 to the x would certainly be an exponential. A would just be 1. Another kind of exponential would be something like 4 times 1/3 to the x. You got to have the x. And I can subtract 3, or I can subtract a number from the back of the function. That still makes it exponential. The key thing when you're looking for an exponential, you're looking for that variable in the exponent. So for every exponential, we have a domain and range for this function. Now if you remember, the domain is going to be all possible x values. So it's all values I can plug in. We had excluded values in Module 5 for rational functions, things that it could not be because it made asymptotes or holes or things like that. But the domain of exponential things, all the possible x values, it's always negative infinity to infinity. So negative infinity to infinity means every negative number, every positive number ever possible. So this is really all real numbers. Okay. The range, which we define range to be all possible y values, it is not always the same. It is always, for a traditional exponential function, it is 0 to infinity. So you cannot have negative numbers. I cannot put any number in for x in an exponential function and get 0. And I cannot get any negative number. I always get a positive number. So always positive. So it's always 0 to infinity unless there is a shift. Okay. Now shifts would always be things at the end of the exponential, like this one has been shifted down 3. So if I shift it down 3, then instead of starting at 0, it would start at -3. So you can always see this very easily for the graph. When we start graphing them, you can see where the lowest is and where the highest is. But the domain is always all real numbers, so that's pretty nice. So let's look at some examples. This first one says, are these functions exponential? So really all we're looking for is the exponent, or the variable in the exponent. So this one would be for sure yes. And again, the real reason, the big reason, is we have this x in our exponent. The second one here, y equals x squared minus 10, hopefully you recognize this is not exponential. Because there's an exponent, but the exponent's a 2. We always want the x in the exponent for it to be exponential. This is actually quadratic. This is what we studied in Module 4 quite a while ago. The last one we have 4 plus 2 times half x. We got our variable in the exponent, so that's good. So this is exponential. If I want to rearrange it, I could also write it as 2 times half to the x plus 4 to kind of see in the traditional way where we have the a, bx, and then some number added or subtracted to that basic exponential. Okay, so what we're going to do is we are going to graph some exponential functions on Desmos, and then we're going to determine what the domain and range of those are. Okay, so remember, we said domain is always going to be everything, and range is going to be 0 to infinity unless some kind of shift occurs. Okay, and we'll see how that kind of makes sense with the graph. So we'll start with y equals 2x, 2 to the x, pardon me. Definitely exponential because it's got its 2 to the x. And so I know right away, I want to know what is the domain and what is the range. Well, every exponential is going to have a domain of negative infinity to infinity, always. And unless there's a number added or subtracted to the end, the range is always 0 to infinity. So because this one had nothing added or subtracted to the end, this would just be 0 to infinity. The only exception is if you multiply it by like a negative number, then it might flip over. But you can definitely see that from the graph. So let's look at the graph of y equals 2 to the x. I graphed this on Desmos. And so you can kind of trace the graph. You can see that it kind of starts off really flat and then really takes off. This is what all exponentials look like. They're very flat and then they go really high. Or they're really high and then they go down and flatten out. So this one is really steady, really flat, and then it really takes off, really goes up really quickly. So you can see that this red line is going to go on forever. So the x values, this will have every x value ever wanted. You can plug in any x value. There are no holes, there are no vertical asymptotes, nothing like that. That's why the domain is all real numbers. Now as far as the range, the lowest this graph goes is going to be right here, the y-axis. You can see it never goes below the y-axis, and it never touches. It kind of flattens out at y equals 0. So the range, the lowest it is 0, because remember range is y, the lowest is 0, and then the y's go up forever and ever and ever as this thing grows. Okay, so our next one is y equals 1/4 to the x plus 1. Now this is exponential, it's got the x in the variable. Now interesting enough in this case, the thing inside that it's raised to this x is a fraction. And so what you'll notice about the graph is instead of going up forever, it's really high and then it really flattens out, Now the domain of this, as I'm trying to find the domain and range, domain is still negative infinity to infinity. Any x value is still good. The range value is going to depend on what's added or subtracted to the end. So in this case, it's 1. So what you notice about the graph, the lowest this graph goes is it really starts to flatten out, not surprisingly, at 1. So it never goes below 1. So it goes from 1 on the bottom and then it goes up forever. So its range, we say, is from 1 to infinity. So this number that's added on the end of your exponential, that's what's going to change your range. That's going to change it to shift up a little bit or shift down a little bit. from your traditional 0 to infinity. So again, it goes down like this, and the reason it goes down versus going up like the last one is because this number, the 1/4, is less than 1. If it's less than 1 and everything gets smaller, it basically gets cut in fourths every time. Okay, so our last one is y equals 2 times 7 to the x minus 3. So domain will be the same, negative infinity to infinity. In this case, we're subtracting the exponential by 3, so the range will be shifted down by 3. It was shifted up 1 in the last example. Here it's shifted down because it's negative. Now here's my graph on Desmos. Make sure you try to graph this. Make sure you can put this in Desmos and you're getting the same graph as me. You can see it goes forever x-wise. It goes left and right forever. But if you see this line where it kind of flattens out, it always flattens out at negative 3, which was that shift down. So the lowest y value you have is negative 3. You see there's no graph down here. There's no y values down here. So it's only from negative 3 and then up to infinity. Okay, so what you've kind of noticed, hopefully, in looking at some of these graphs, is that they do have an asymptote. Okay, remember asymptotes is a line where the graph approaches but does not touch. Now exponentials, so we can say an exponential function, we'll call it f of x equals a times b to the x plus c. So we have the basic exponential, and then I'm going to do my shift, or up or down, like be positive or negative c. So this always has no vertical asymptotes, but a horizontal asymptote of y equals c. So just like we saw with the range, this thing flattens out at whatever that number, that shift is at the end. Well, that flattening out makes a horizontal asymptote. So these always have horizontal asymptotes, and it could be 0, but they never have vertical asymptotes. So let's look at a couple of examples. So this first one we want to see, and these are just the same graphs we did before when we did domain and range. We're just going to do horizontal and vertical asymptotes. So we have y equals 2 to the x. So exponentials never have vertical asymptotes. They always have a horizontal asymptote of y equals whatever your shift is. Well, 2 to the x has no shift, so this would just flatten out at y equals 0. And if I look at my graph here, this is the same graph we had earlier. If you imagine a kind of dashed horizontal line right at 0, this graph definitely kind of approaches it. It gets very, very close to it, but it does not touch it. So really everything, the asymptotes, the domain and range, everything's really based on that shift. Everything else for an exponential is very consistent. So here's our y equals 1/4 to the x plus 1. So again, no exponential is going to have a vertical asymptote. So the horizontal asymptote of this, it's always based on the shift, which is 1. So the horizontal shift asymptote is y equals 1. And looking at the graph, that should make sense, because there is a horizontal line that the graph will approach, but not touch. All right, finally our last one, we have no vertical asymptote still for this one. And a horizontal asymptote, we said that this one is going to be at y equals negative 3 because our shift is negative 3. And if you look at the graph down here, a very clear flattening out of the graph here at negative 3. So, a really nice section introducing exponential functions, this growth by a certain factor that gets multiplied every time. We will eventually solve equations and do some applications of these kind of exponential functions. For now, go ahead and try assignment 2, and let us know if you have any questions.